Okay, so now let's look at some practical examples for two-stage to orbit. And as before, we need to choose inert mass fractions from the real vehicles. And so here are some practical numbers for, say, a first stage hydrogen LOX, Fi inert, 0.095 or 9.5%. And here's kerosene LOX, 0.07 or 7%. So these all depend on the propellants being used, and that determines the kind of structure you need to hold onto these propellants. And so we take these from actual cases and can compute some numbers. Now remember that when you have a two-stage, what you have to do is look at the breakdown of the delta V. All right, so the delta V will be composed of F1 times delta V plus F2 times delta V. Delta V is the total. And so if you devote a certain fraction, say 0.46, to the first stage, then the remaining fraction, 0.54, will be devoted to achieving this delta V in the second stage. And so in order to find the best fractional values to use on the first and second stage, we can plot the first stage delta V fraction, F1, against the initial mass. That's the total mass of the vehicle stacked up. That's the two stages fully loaded. And find this curve, and we look for the lowest point in there, and we get the minimum initial mass, and it happens to be at F1 is 0.46. And that value is a little bit over 14,000 kilograms if the mass of the payload was 1,000 kilograms. So this is the process to find the best breakdown or allocation of delta V in the two stages. And if you perform that for various two-stage vehicles, you get from SPAD the following values. Now let's just pick the hydrogen LOX case and work down this column. So here we pick for the first stage an ISP of 410 seconds, and for the second stage an ISP of 435 seconds. Now why is the second stage more efficient? That's because at higher altitudes with lower ambient pressure, the exhaust velocity can be a little higher because the atmosphere is not slowing down the gases coming out of the nozzle. For stage 1, we're picking an inert mass fraction of 9.5%. For stage 2, 10%. Again, this has to do with the specifics of the actual hardware and the typical numbers that come from the rocket industry. We have decided to pick as our example, well actually we have minimized the total mass by picking for stage 1 4,140 meters per second, and the remaining of the 9,000 meters per second, 4,860 to be performed by the second stage. So these two add up to the 9,000. The first stage had a propellant mass of 9 kilograms. That is, again, using the 1 kilogram as the payload for the SPAD analysis. For our case of 1,000, we just multiply by 1,000 all of these numbers. So it would be 9,066 for a payload mass of 9,000. The inert mass would be 952 kilograms, and the propellant mass would be 2,668 for the second stage. The second stage would have an inert mass of 296 kilograms, and the total initial mass would be 14,106 kilograms if the payload mass started at 1,000. But in SPAD, they assume the payload is 1 kilogram, and so you just multiply by your payload to get your final numbers. Notice that we get 7% of the vehicle is payload. That is essentially taking 1,000 and dividing by 14,000. That's 7%. That's a pretty large percentage. Okay, so that's very good. This is large and good. If you look at the hydrogen kerosene combination, notice that we get we get a much bigger vehicle, 20,000 kilograms, and about 5% And for the hydrazine and liquid oxygen, about 5% is payload. If you look at solid rockets, only about 1%. So in other words, you'd have an 81,752 kilogram vehicle to launch 1,000 kilograms. Only 1%. I would consider this, let's say, okay, if not poor. Okay? So not particularly attractive to use solids. So that concludes the presentation on propellant considerations for launch vehicles.